Press the go live button.
Sure.
Go live.
Do you want to remove the people faces from?
Wait,
Yeah, that's a good question.
Who am I speaking to? I mean, what am I speaking into?
You.
This microphone?
Uh.
Oh, yeah, microphone. Oh, it should be closer.
Yeah. Speak. You speak. Make sure it goes.
Hello?
Yep. That seems like your voice being picked up. So now YouTube can hear you. The question is, can the other people on the Zoom call hear you? Can the other people on the Zoom call hear it when Nerla talks?
Hello?
Can you say something again?
Hello?
No.
Yeah. Can you talk again real quick?
Hello?
You're not.
No.
Okay.
Do you want to just put the mic closer to her?
The problem is they can't hear this mic because they're on Zoom.
Wait, how did they hear anything at all?
Okay,
Well,
I mean,
presumably they
like
can
if
hear
the
you
talk
through
is on
Zoom.
Google Drive, maybe you guys can just like switch laptops like for the talk, and or just have your laptop close to hers so she can hear her.
Okay. If I like put.
Oh no.
Okay, yeah. Have the laptop close to her, but then the camera's still facing you, Bolton, so that it's not like a double camera.
Okay.
What? Hello? Can you hear me?
I can hear you a bit.
Super faintly.
Okay.
Very
Here's what I'll do. I'll go to the mic on Zoom, and instead of the mic on Zoom being my own computer, the mic on Zoom will be the room mic. Okay.
Hello?
Now,
Hello?
can you hear anything now?
Yeah.
Yeah.
Okay. Hi, everybody. My name is Nerla, and I'm going to be talking about this paper, ZeroTrace Oblivious Memory Primitives from Intel SGX by people. So, so the whole point of this paper is to kind of explore how do you execute this protocol, Oblivious RAM, obliviously in SGX. So Oblivious RAM is this data structure or scheme, and it's used to store and retrieve blocks from blocks of memory on a remote server such that the server learns nothing about the data access pattern. So you have a user here and you have an untrusted server. That user is trying to read some data at position 1, and it contacts the ORAM on the untrusted server, and this untrusted server doesn't know like which piece of data is at position 1, and then the user gets that data back. So the simplest solution for this to get this kind of security guarantee is just to send that user the entire data set. So if you just send the user all of the data, then the server doesn't know like which piece of data it was wanting to access. But we don't want to do that because that might be a lot of data to transmit to the user. So one construction type of ORAM is tree-based ORAM. So in this kind of construction, the data is organized into a tree data structure. So each leaf has some different piece of your data in it. And then there's a position map that stores a mapping of the key to the position in the tree. So here on the side you see like saying A is on this leaf 3. And when you want to read some data, say for example you want to read this piece of data, you have to look at the position map, read it, and then update the location of that data so that the server doesn't know the location that or the piece of data that you actually wanted to read or write. So this is kind of different than what we're used to because reading a piece of data would update the data structure. So this the ORAM guarantees that we want require an ordered sequence of read and writes, And that guarantee is that given an ordered sequence of read and writes, the server is not able to distinguish like two different sequences from another. So we're trying to run ORM in SGX. So what is SGX? So SGX, it allows users to privately execute code on an untrusted server. So if the user wants to execute some function, it can execute it on an untrusted server and get the result back. And so one thing that you might want to do when you're executing your code on this untrusted server is that you might want to read some user data. So we can see that like ORM can help us kind of hide which piece of data we're reading when we're executing our code privately in the SGX enclave. So the security goals of this paper is to protect against an active software level attacker. So in SGX, that means we want to prevent side channels and we want recovery and security across terminations. And we're not concerned about these other kind of attacks like power analysis or denial of server or compromising SGX itself. So what are side channels in SGX? So the basic idea is that an adversary on the untrusted server can learn or observe some information about the enclave execution to learn about the execution. So you can think of two types for this work that they're concerned about, which is execution time and memory access. So if you look at this kind of pseudocode here, if you're taking some secret input into this function, if the secret is 0, then you're going to be executing for a long time, versus if it's not, it will end quickly, so that will kind of leak what the secret is. And for memory accesses in SGX, there's a structure called an enclave page cache, which is an isolated section of DRAM. So the data in the enclave page cache is like storing the code that you're executing and the data that you're running on. So this data in the enclave page cache is encrypted, and so when you are running your program with SGX, only the CPU can like decrypt this enclave page cache and run the code, and the untrusted server is not able to see that. And same with the data. And so this EPC is like a hardware defined thing, and its size is limited. And so because its size is limited, you have to implement paging. And when you do paging, you would switch out different pages of memory that you want to access. So when you're doing this paging, you would encrypt and integrity check the piece of data that you're swapping in and out of the EPC. And this, importantly, like reveals some page level access pattern for your paging stuff. And it's kind of expensive because you have to encrypt everything and do the integrity check. So when we're implementing ORM, we can't just naively put everything into the EPC because the size is limited, and it also has this problem of like you might end up revealing some kind of access patterns in your ORM. So the way that ZeroTrace approaches the timing side channel problem is to kind of make sure that they implement their ORM memory controller correctly. So the ORM memory controller is responsible for getting the logic of when you're updating your position map. So they use this x86 instruction called conditional move, cmove. So this basically allows you to move this source data to this data located at SRC to DST if this condition is met. So the way that they use this is to implement this OU update function that basically does the same thing but to like storage. So this pseudocode is showing how they would do their leaf label retrieval. So what this leaf label retrieval does is it reads the leaf, samples the new location that the leaf is going to be in, and then updates the leaf to that new location. So this is doing the like picking in the position map where the information about this new location is stored. So if we look at the code, it goes through the every position in the position map, and if it's like the new location, if it's the leaf that we want it to update, so if I equals ID, where ID is the ID of the data that you're trying to access, it looks at the position map, the location in that location in the position map, and if it's equal to the ID, then it would update the leaf, and if it's not equal to ID, it would just it would not update it because the condition would be false. So here, the first one, it's like updating it if condition is the first one, it's not updating it because position map I is what is already there. And if the condition is met, then the new leaf is moved to that position map. So it's important to note that you're touching each location in the position map, so you won't be able to like distinguish which position was actually updated because you're doing this OU update every time. You're doing it for every position in the position map.
Could you go back over the EPC and maybe the connection to this? So something that's not so clear to me is whether or not access patterns of things in the EPC are seen to the attacker or not.
Yes. So they have something where they basically limit the size of the ORM controller to make sure that it fits inside of the EPC.
Okay.
So we have a question also from the YouTube asking, is the encryption key kept within the CPU?
Yes.
How big is the EPC that they try to stick within?
So the data that they have access to is 95 MB.
Okay.
And then there's some like metadata that they're like factoring into that.
And so is the problem that, so among those pages, and then like maybe then on the next slide, right? So on the next slide, they loop over all the things in the position map. I'm not clear, is the point that the position map then fits within the EPC?
So this is kind of thinking about this timing side channel stuff, not really like the memory. So this point of the C move is that when you're updating the position map, you won't be able to tell which position you updated. And then basically, so for this memory access, they're just going to say, okay, we limit the size of the position map to fit in the EPC, so it doesn't matter whether or not like you're leaking some kind of memory access while doing this update.
Well, okay, so I mean, if I understand it right, then having this loop over the entire position map is useful because, I mean, you only need to do that if the EPC leaks access patterns. Or to put it another way, if everything in the EPC could be accessed without revealing which thing in the EPC was being accessed, then it doesn't seem like you would also need this. And then if that's the case, then the EPC isn't relevant to the security model then.
Are you asking if the position map itself needs to be encrypted and stored in an ORM of its own, or?
Well, I mean, you don't need to go there looping over all of it.
Which, if it's stored in an ORM of its own, then you kind of have to loop over a bunch of it anyway, right? I guess if it's stored in an ORM, then you don't have to loop over all of it because you just recursively do the same thing.
I mean, if it fits in the EPC is already an ORAM, if it's the case that the EPC does not reveal the access pattern, so that's what I'm asking.
So this conditional move is to like make sure when you're updating something, so like the use of the conditional move allows you to like update each position. So you're updating it twice. You're updating it with the new value or you're updating with the old value.
Mm-hmm.
So I think like without this, they would say, so if this is equal to, if the position is equal, then update it, else don't update it. So I think they want to avoid using like some if-else statements to update the position map. And like, I guess also computing this condition, actually I guess they already compute it here.
I mean, you have to still re-randomize every position in the position map unless you're using an ORM, right? Like,
I mean, it seems like whether or not you need to depends on the model, and I'm just trying to ask to clarify which of the two cases the model is.
like unless the position map is stored entirely in EPC, like the whole time, it needs to be written back to untrusted storage, right?
Okay, but if it is stored in EPC, then you don't.
Yeah.
Okay. So is the assumption, I mean, so then, I'm not sure that's true, so like that, I don't know whether the EPC should be considered to be, I mean, let me put it this way, like the,
So you're trying to get like if this conditional move thing kind of replaces, is necessary if the position map is stored in the EPC.
yeah, that's my question.
It can be probably stored in the EPC, right? Like it's just not big enough.
Well,
To
they have
store
like
the
something
entire-
else to address that. So like what they said is that the logic that decides which position to update is like the critical logic. So from that that sounds like they're saying if there's some kind of timing side channel in the logic that decides which position to update, then you kind of need this conditional move. It's not saying that like actually doing the update is what is going to leak the side channel, I guess. It's like kind of like doing this this if statement here, if I equals ID.
That limit of like around 90 megabytes is true of old SGX, but newer SGX, like SGX2 supporting processors have a much larger EPC. So it could be that there was something like this that was necessary when the EPC was very small, but becomes not necessary when the EPC is much larger.
So are you saying with a larger EPC, you can store the position map?
Entirely in the EPC, right?
Yeah, and then you don't have to worry about the access.
Well, maybe. I think you still might, because I don't know that the EPC actually hides access patterns or not.
Let's see what I write. So I think they said paging reveals the access patterns. That's what I wrote here. So to me that says if something is in the EPC, you can access it freely. So maybe I'll just keep going.
Sure.
Yeah, so this is what they were saying. In the tree-based ORAM, you only care about hiding the process of deciding which leaf is being accessed. So actually what they said is that you can have the untrusted code do the actual fetching, but you want to hide the deciding of which leaf is being accessed by having it in ORAM, or in SGX, and in the EPC. So they basically make sure that the memory controller, which includes this like logic to update the position map, is tailored to fit inside the EPC. And then yeah. And then they have this like idea for this recursive construction where they have the position map, if it's too large, it uses an ORAM to store the position map, and then you have the position map is in the EPC. And then if you and the reason that's kind of more that's smaller is because the position map is smaller than your entire ORAM data structure, so its position map is smaller than itself. And so like they actually say that, but like you can keep doing this recursion such that like the position map is that this position map that you're actually storing in the EPC is like small enough to fit in there.
Do you think the reason that they presented it in the order that they seem to have presented it so far, because they're aiming this like paper at not cryptography audiences, because this recursion, like this recursive construction has been like well known in the ORAM literature since the 80s or something, right? So like I'm curious, like it seems like what they're saying is, whatever client code would run on the ORAM, the insight is that you need to run that within the EPC, the entirety of the client code, and here is how you can like optimize it to do it without the recursion. Like I guess I'm curious why they present it even without the recursion in the first place, because like I guess these techniques have been known, right?
I think like they want to like emphasize like running something in SGX, just running that client code naively in SGX is not going to just give you the same exact guarantees. You have to like think about memory access and side channels when you're like handling the position map. And then they're kind of like pointing to other papers to say, okay, we reduce the size of this using this recursion thing that is well known. Okay. And then the next thing that they kind of talk about is about termination SGX. So the thing about the enclave pagecast EPC is that its state is lost if the enclave is terminated. So you have to do some kind of persistence of this state to disk in order to like recover from termination. And then without this, there's the possibility for replay attacks where the untrusted host can like return stale data to the enclave. And we know that the ORAM guarantees are only based on a sequence of reads or writes. So like if you take the same ORAM state and run read on it, it will probably like give you two states as a result. And then basically like looking at those two states, you might be able to discern, like break the ORAM guarantees. So the way that they kind of prevent this is to have the users use a nonce to sequence the ORAM accesses so that it always has to be executed on the freshest state. So you have to like make sure that this nonce is equal to the version of the ORAM user data. And this logic is done in SGX, so it like you can't fake that.
So is there like a place where the version persists?
Yeah. So each time you're like reading changing, doing this update where you like kind of change the position of the leaf, that's going to have like a version number attached to it. And so like in the case like your enclave data is corrupted, you kind of have to replay all of the past queries or requests to get to the current version and do more requests.
Where do the replay attacks come from? I mean, does this presume a particular use of sealing files?
Yeah, so they basically say that the actual tree like is stored in the untrusted stored on disk, and so after you kind of decide which leaf you're going to access, you're free to like tell the untrusted host to like read that leaf. And so
I see.
You can do a replay attack because like you can read some older version of the leaf, I guess. Yeah. Yeah, that's it.
Can I ask another? So, like, maybe I'm missing something here, but it seems like in some, there's at least one sense in which the replay attack is like gonna not be preventable at all. So, like, let's say that I have some program running in SGX that's like only supposed to allow the outside user to like read like one piece of data, like one arbitrary piece of data of their choice. It seems like there's nothing that a replay, like what actually can be done to prevent that sort of attack for like a replay attack. Because if I just like reset you to the time when, if I reset the enclave to the time when it hadn't yet given me any data and was still like, ready to give me data, in theory, like then it would presumably give me like an additional piece of data, right? So is there I guess maybe what I'm asking is like they all of these things come with version numbers, but how does it know that how does it know that the version number isn't just reset? Is the version number stored somewhere in the enclave itself?
The version is stored like with this data. So like this tree data structure is stored on disk, and then you might have like V1, V2 on this leaf node or something. I don't know.
Okay.
And then it knows the version because the user has to tell it.
Right, because it touches. So that I guess the point is that it always has to touch the root to like ever do any ORAM operations whatsoever, and the root will hold like the correct version number, and so it won't see the right version. Wait, wouldn't wouldn't the if it's stored in the This is stored on disk?
Yeah, the
It's
data
sto-
structure. Yeah.
Okay, but so if it's stored on disk, the disk is the part that you can, in theory, like overwrite and reset to the previous version, right? So I guess like we're just sort of somehow assuming that that doesn't happen.
So like when you're doing the request, like you have to see what version the request is. Like,
What version the request
let me see
is?
if I think I have this. Like this read has like a nonce I here, and then the enclave is like saying, okay, I want to update the leaf for version I of the data,
Okay,
or I want to read that version of the data.
I see. So like it's basically a different version of the data for like every time it updates the data is like a new version of the data. And so that's how it can like basically keep track of the total number of reads that it's done and like the whole existence of the program. And then if it like restarts the program from some point, it's going to like keep track of that. Okay, I think that makes sense.
Yeah, so if you just like terminate it, it can just like, it doesn't have to replay everything because it just has the latest version. But then if you
Yeah.
lose the data or something, then you have to replay everything.
Play all past requests. Yeah, okay, makes sense. Let's see, any questions from the YouTube?
For this one, like, so there's like a few like functions that they say like they need to use this update for. So I think it really is about they're worried that without this conditional update, there's going to be like a side channel, a timing side channel, not a data access side channel, or memory access side channel. But I guess maybe it's a combination of those two things. Okay.
Yes, I guess this is just if you want to do naive ORM for the position map. That's what
Yeah,
this is.
so they basically talk about how to implement like path ORM and circuit ORM. So path ORM has like a stash that is kind of like a cache of like what the last piece of data that you accessed. So in order to update the stash, they do something similar where they're like technically updating every position in the stash, but it's using OU update. And they do mention like the stash should be in the EPC.
they have experiments? Like, are there certain, like, what are the relevant, like, break-even point questions? Like, how large of a database, like, how does the size of the database affect, like, which approaches are most appropriate, and is there a trade-off of, like, number of keys versus the size of each value?
Yes. I can look at the paper. I don't have it in the presentation, but
Yeah, they don't have a comparison with like completely naive linear scan break-even point, which would have been nice to see.
yeah, so their evaluation is about, I guess, comparing circuit ORAM and path ORAM performance.
Is circuit ORAM the square root ORAM? I feel so knowledgeable. I've taken David's course, so now I know like all the different ORAMs. Now I know what ORAM is. But like, so like, what is circuit ORAM, and does it differ from like path ORAM? I know path ORAM is like the really good, like logarithmic efficient one.
Circuit ORAM is also logarithmic. The eviction function is just changed so that it's optimized for circuit complexity instead of
Okay.
just plain time complexity.
Sure. Okay, cool. I guess I'll end the stream. Thanks all YouTube people for joining.